Alright, welcome to CSM worksheet 10. Is it worksheet 10? Worksheet 10 question 3 walkthrough. This is one of the harder questions on the worksheet, which is once again worksheet 10. I have to remind myself about that. So let's go through the question, and let me preface this walkthrough with what this question is supposed to be about. So this question is supposed to address what is a projection of a vector, and what that means is, well, there's a special thing about vector is that I'll actually talk about it later, never mind. Let's just go into the problem first with the exploratory part, which are part A and part B, and then I'll talk about what projections are, because then it will probably be a little more clear. So, let's look at question A. Suppose we have the following vectors, v and v star, where v star, here's a typo, has a 0 second component and a non-zero first component. Write down the information we just got. V star is equal to v1 star 0. Okay, if v is a linear combination of v star and another vector perpendicular to v star, then what is the coefficient of v star in this linear combination in terms of v and v star? So, what we may do is to first try to understand how the problem is set up. Here, we see that I need a scalar multiple of v star, which I'm going to write as alpha v star, and a vector that's perpendicular to it directly, which is v perpendicular that I'll write here. These are perpendicular, such that they add up to v. So there are two things that we can infer. First of all, v perpendicular is still perpendicular to v star, because v perpendicular is already perpendicular to a scalar multiple of v star. If I don't deal with the scalar multiple here, I could just shift the I could just shift this entire vector here, and v perpendicular will still be perpendicular to v star. So that's not a problem. We are still complying the problem description. So now the other problem is, how do we find the coefficient of v star, which is alpha? So to deal with that, we have to write out a little more information to guide us to the true solution of the question. Say v is equal to alpha v star plus v perpendicular. So that's going to bring us to the conclusion that this vector v1, v2 is equal to alpha v1 star 0 plus v perpendicular 1, v perpendicular 2. There's another thing that we want to take care of, which is these two unknowns. They're annoying. But here's a trick. V star is a vector along the x-axis, and v perpendicular is perpendicular or orthogonal to v star. So that must mean that v perpendicular is a vector along the y-axis. That means its first component is 0. So I get that v1 is equal to alpha v1 star, and v2 is just equal to v2 perpendicular. So then I can derive this identity around alpha, saying that alpha is equal to v1 over v1 star. Okay, so that's our solution for part A. But we're only solving for the case where v star is on the x-axis. What if v star is not on the x-axis? So that's going to be what we're going to deal with in the second part of the question. Suppose we have the following vectors w, w prime, where once again w and w prime are now, none of them are lying on the coordinate axis. If w is the linear combination of w prime and another vector perpendicular to w prime, what is the coefficient of w prime in this linear combination? So I'm going to borrow the setup from last question and draw out a scalar multiple of w prime. Let's say beta w prime that is directly perpendicular, and that has a directly perpendicular vector that, oh my god, my hand, that can add up to w. So I'm going to call this perpendicular vector w perp, which will be written in this way. So information tells us that w is equal to beta w prime plus w perpendicular. So now now once again, let's remind ourselves that our end goal of the problem is to find the value of beta. But to find beta, I probably have to base it on some kind of scalar value to work with. There's still a lot more information that we can retrieve from this problem. one thing is that, first of all, beta W prime and W perp are orthogonal to each other. They form a right angle. So together with W, which is the sum of two vectors, this entire setup becomes a right triangle and allows us to use trigonometry. Say that the angle between W and W prime is theta W comma W prime, and that will also be the angle between W and beta W prime, because beta W prime and W prime are on the same direction. So it turns out that using the law of cosine, we can extract an information that's written as follows. Cosine theta of W prime is equal to W dot W prime over W prime times the length of W times the length of W prime. Or this is what we call the magnitude. And then we also know that since this is a right triangle, the length of beta W prime is supposed to be equal to the length of W times the cosine of theta W prime. So it turns out that now we have two extra pieces of information from the last setup, and this will probably allow us to derive beta. How so? First of all, let's notice that the right-hand side of the equation derives into W length multiplied by a fraction whose denominator also has the length of W. Second of all, since this is a norm of a vector, and more specifically, it's the norm of a scalar multiple of a vector, I can move the scalar multiple out. And then what I can do is I can just divide both sides of the equation by the length of W prime, and I would have ended up with an expression of what beta is. So in this case, beta is equal to W dot W prime over length of W prime, length of W prime. So I'm going to square it. So we got a value for beta here, using the law of cosine. Alright, so now we have completed both questions. Well, what is the significance of completing these questions? Well, first of all, let's try to see if the general case here we derived in part B applies onto part A. So in part A, we are trying to say that alpha is equal to V1 star. What if I substitute a formula from part B to part A? In this case, I'll see that alpha is equal to V dot V star over V star length squared. So that's going to be equal to V has the first component of V1, V star has the first component of V1 star, V star has a 0 second component, so that's not gonna affect the dot product here. Meanwhile, the length of, well, V star itself is just V1 star 0, so the length of it is also going to just be V1 star squared. The V1 star at the numerator and denominator cancels out, and that grants us the exact answer we got in part A. So we do see that the general case solution we have here is applicable to the special case noted in part A. Okay, so what's the deal with the coefficient? Why are we finding the coefficient? Well, let's look at a perspective here on part A and address the problem. Suppose once again I have a vector v and another vector that is supposed to lie here, and say that I have a light that hits right from above to below. Then what is the vector that lies on the ground when, what is the shadow of v when it's stricken by this light that comes right down? Or in other words, what is the projection of v onto the horizontal x-axis? If v is a vector, if v has a component along this horizontal axis, how long would that component be? So that was the problem we're trying to solve. For example, we figured out that the length of this component is supposed to be equal to alpha v star. So if we know the direction, we can just say that the length of alpha v star is equal to alpha times the length of v star, And we also knew what alpha is by solving the problem. So in this case, we can indeed see what is the magnitude of the component of V that lies along this horizontal axis. Or in other words, what is the length of the shadow once there's a light striking on V such that its shadow is completely reflected onto the ground we see here on the horizontal axis. So this kind of problem, which is usually solved geometrically as we have done, is called a projection. So we'll talk about the definition of projection later, but now let's try to complete part C, which depends on part B. So to defend our answers in part B, suppose the solution you have in part B can be expressed as a variable x star. Then prove that such solution x star presents the smallest possible value for the length of w minus xw prime. So in other words, we're trying to prove that for all, say that x star is equal to the solution we got in part B, which would be the value of beta, that is w dot w prime over the square of length of w prime, then prove that for all x, the length of w minus xw prime is larger or equal to w minus x star w prime. So that's what we're trying to prove. So, the length of a vector is very ugly. It contains square roots, but one special thing about this is that the length of a vector is always non-negative, which means if we simplify the prompt a little so that it's a little more doable, we prove an equivalent prompt that says for all x, the squared length of w minus xw prime is larger or equal to the squared length of w minus x star w prime, then we will still be proving the same thing. And the reason of that is because the length is always positive or 0, which means that I don't have to worry about the case where maybe the length of a vector is -1 and squaring them reverses the sign of the inequality. So we'll be proving this simplified prompt from now on to prove the original prompt that we have here. This is about simplifying the thing that we were supposed to do in the question. So let's try to see what the value of w minus xw prime could length square could be. The square of this length is also equal to the dot product or the inner product of a vector with itself. So I'm going to write it like that. And I'm going to expand this equation such that it is later equal to w transpose w minus x times w transpose w. Actually, it turns out that we have two of these terms, plus x squared w prime transpose w prime. Keep in mind that w prime and w are both known variables. So essentially, we're working with a quadratic polynomial. And we're trying to minimize a quadratic polynomial. Well, I bet we have heard of something that can come of use when we're trying to minimize a quadratic polynomial. Well, what do you think it is? Yes, unfortunately, it's calculus. So let's try to do calculus to find what x minimizes this expression. d dx of this polynomial is then equal to, well, let's just do the derivative of this expression up here, 2 w prime length squared x minus 2 w prime transpose w. And if this is going to be equal to 0, if this derivative is going to be 0, then we find a critical point. And one other interesting thing we find is that, well, this is a quadratic polynomial, but not only is it a quadratic polynomial, it is a face-up or concave up quadratic polynomial, which means its shape is like a U that opens up. And that means you only have one minimum point on this quadratic polynomial. So if you find a critical point, that's just going to be the local minimum. That's just going to be the global minimum of our entire function. And keep in mind, once again, that at the critical point, the derivative is supposed to be 0. So we end up at this expression, where if I have x min being the input of my derivative function, then the derivative is going to be equal to 0, such that the critical point happens. So we end up having the minimizing x is equal to w prime dot w over the square of length of w prime, and that happens to coincide with what we find as x star. These two values are equal. There are a lot of ways to prove that these two values are equal. Well, one of the first way is to use your eyes, and the second way, well, actually using your eyes is probably the most convenient. You can see that the mathematical expressions are the same. So we do indeed prove that the value we find in part B minimizes the distance between w and a scalar multiple of w prime. In other words, beta minimizes the length of w transpose, because this length is directly equal to the length of w transpose. So that's one special implication. And now let's actually talk about what a projection vector is based on the context we have here. The projection of a vector x onto w, which means I'm projecting a vector x onto the direction of w, is the vector in the direction of w, yeah, because you have to project onto the w direction. So in other words, the projection is going to be a scalar multiple of w, and the projection has the magnitude of beta, which is exactly what we found before. It's going to be w dot x, which is the w prime dot w here, over w dot w, because w is the projection we project on. Versus when we see in the previous part, we're projecting w onto the direction of w prime, so we have w prime length squared at the denominator, and that's also what we see in this expression here. This is the closest vector to x along the direction of w. What does it mean? This means that this is the vector that minimizes the difference between x and its projection. The difference between x and its projection onto w can be written as the difference between x and beta w, where this beta w is the projection of x onto w. Do we see something very similar in the previous part? That the projection of a vector is supposed to minimize the distance between the vector and the direction being projected onto. So in the end, we do see, so consequently, we see that by completing the first three parts, we have actually completed a proof on what is the magnitude of the projection of a vector onto another. So just completing these three parts would have made a standard CSM question, but unfortunately the maker of this content question is like, I don't know what he's doing, but he decided to like design 3 more subparts, so I guess we'll go through it. Now part D. Suppose instead of projecting vectors onto another vector, I will now project vectors onto a span of vectors. So here is the span of vector. Remember that the span of a vector is supposed to be a set of vectors, which is why we're using this curly S to denote a set of vectors. So now we try to propose a method of finding the projection of a vector onto the span. So I'm going to kick things off here by first assuming that S is going to be a plane. So say that S is a plane, and this vector 2, 2, 3 here is a vector that we'll all call V. So the vector comes out of this plane. It does not belong to the plane, meaning it doesn't lie on the plane. But I want to find the version of V, or the projection of V, that lies on the plane. Let's call the projection W. W is going to lie on the plane, which means W is going to belong to S. W therefore belongs to the span of 1, 2, 0, 1, 0, 0. So it is a linear combination of 1, 2, 0, and 1, 0, 0. If it's a projection, then the difference vector v minus w must be perpendicular to w. What does this mean? This means that v minus w dot any vector belonging to the span, such as 1, 2, 0, well, this v minus w is perpendicular to w, and then it has to be perpendicular to the entire plane because there can be so many w. That is the difference between there's one w that is the projection of v onto the plane, and v minus w, the difference between these two vectors, must be perpendicular to w. W happens to be a linear combination of 1, 2, 0, and 1, 0, 0. So let's say for a more concrete case that w is equal to alpha 1, 2, 0 plus beta 1, 0, 0, then the difference v minus w dot alpha 1, 2, 0 plus beta 1, 0, 0 must be 0, because these two vectors are supposed to be perpendicular to each other. But then this evolves into an interesting issue, which is that if you're perpendicular to a linear combination, or even to the entire plane S, then shouldn't you just also be perpendicular to the component vectors of the plane? There's another mathematical way to show this, but I'll stop at the conceptual level here, because the mathematical aspects are already explained in the solution file. So the TLDR of the previous 3 or 5 seconds of rambling about what to do with the difference of the vector between vector and projection is that the difference between vector and projection must be perpendicular or orthogonal to this S that we're dealing with here, that we're projecting onto. So we end up getting that v minus w dot 1, 2, 0, which is a vector in the span, is 0. And v minus w dot 1, 0, 0, which is another vector that belongs to the span, is also equal to 0, such that v minus w can truly be perpendicular to their linear combination, that is w. Okay, so now that we have went through that, let's try to find w. And keep in mind that we also know that v is equal to 2, 2, 3 here, based on the prompt. And that is the vector that we're trying to project onto S. I'm going to combine these two linear equations together and put them in matrix multiplication form, which you are probably slightly familiar with after Module 1. So if I combine the two equations into this matrix vector form, what it means is 1, 2, 0 dot v minus w is 0. 1, 2, 0, v minus w. V minus w is a vector. Okay, and 1, 0, 0 dot v minus w is also 0. So this is actually a 0 vector here, which is equal to just 0, 0. Okay, so now that we have understood why this matrix vector multiplication notation works, let's try to actually derive the value of this. So first of all, I'm going to fill in the values of v, so that this is relatively easier to deal with. It's going to be 2 minus w1, 2 minus w2, and 3 minus w3. So actually, I can get this a little easier. Let's say that we revert back to v minus w instead of writing this entire complicated expression. I can also write this equation as 1, 2, 0, 1, 0, 0 v minus 1, 2, 0, 1, 0, 0 w. So in the end, I'll get that 1, 2, 0, 1, 0, 0 v is equal to 1, 2, 0, 1, 0, 0 w. Okay, now keep in mind that w is a linear correlation of 1, 2, 0 and 1, 0, 0. What this means is that w can also be written in the form of 1, 2, 0, 1, 0, 0 alpha beta. This then ends up being the expression that we have above here. So I'm going to simplify w into the above form. And now we have some interesting equation that we can play with to find alpha beta. So in this case, I can first try to multiply the right side of the equation together. So I'll get a 2 by 2 matrix. That's going to be 5, 1, 1, 1. So this 5, 1, 1, 1 times alpha b is equal to 1, 2, 0, 1, 0, 0 times v. Very fortunately, this matrix is invertible. So I'm going to make the inverse of it and multiply both sides of the equation by its inverse. At the end, we'll get alpha beta is equal to is first of all the inverse of 5, 1, 1. So that's going to be, I'm going to use my speed formula here and multiply by the matrix that we mentioned before times v. And v is 2, 2, 3. So at last, I'm just going to do mechanical calculations, and I will end up saying that alpha beta is equal to 1, 1. So in the end, we get that w is equal to 1 times 1, 2, 0 plus 1 times 1, 0, 0, which is equal to 2, 2, 0. And this is the projection of v onto S, or the projection of 2, 2, 3 onto the span S. Okay, that was quite a procedure. Let's move on to part E. So in the end, we also got another formula about how to project a vector onto the vector space, onto a set of vector, or onto a span. But unfortunately, that is not really related with the next part of the question, which is part E. Suppose I have the following line: 2x plus 5y is equal to 0. Find the closest distance between this line and the point 5, 2. Now, this does look like something you'll do in high school geometry, but I do not remember the way that we have done it in high school geometry, so unfortunately I'm going to have to use some linear algebra here to figure things out. First of all, I have an interesting thing that I want to tell you, which is that this line can actually also be imagined as a set of vector. This, let's say that the line is equal to L, then this is also equal to the set of vector, such that 2, 5 dot xy is equal to 0. And this is what the linear equation says as well: 2x plus 5y is equal to 0. So I know that the line can be phrased as this, and furthermore, for each line, for each vector that belongs to the line, that vector is perpendicular to the vector 2, 5, because their dot product is 0. So let's think about a way to get the point 5, 2 involved in this question. So my shortest distance, first of all, what I discover from here is that the shortest distance between a point and a line should be expressed as something that's perpendicular to the line itself. For example, this line 2x plus 5y equals 0 might be drawn as some line like this, and 5, 2 might be a point here. If I have a line segment that represents the shortest distance, then it should be perpendicular to the line 2x plus 5y is equal to 0. I notice that the only vector that is perpendicular to every single point on the line is 2, 5. So therefore, this shortest distance here is some multiple of 2, 5. So this is also writable as alpha 2, 5. And I'm going to say it's the length of it. So let's look at what we can do here. Say that we then can observe that we suppose that we have a point along another place of the vector. For example, say that we know that this vector is supposed to So say that we know that this line is supposed to pass through a point that is the origin, because 0 plus 2 times 0 plus 5 times 0 is also 0. And we connect 5, 2 to 0. Then the shorter distance, alpha 2, 5, is essentially the projection of this hypotenuse here, which I can call v, onto the direction of 2, 5. So alpha 25, which is the shortest distance, is equal to the projection of v onto the direction of 2, 5. And I already know that the projection of 2, 5v is, according to our previous formula, supposed to be equal to the square of length of 2, 5 times the dot product of 2, 5 and v. And I multiply it by the vector 2, 5. Such that I can find the projection of it. Or actually, since this itself is already the magnitude, I should multiply it by the norm version of 2, 5. But we have actually encountered that already in the original formula, so we're actually just multiplying by 2, 5. I am stuttering. Okay, so let's try to calculate this value, where alpha is directly equal to this constant here, and 2, 5 is just equal to 2, 5. So we can notice that v is actually equal to 5, 2, because it's a vector that goes from 0, 0 to 5, 2. So alpha is equal to 25.52 over 25.25. So that is equal to 20 over 29, which means that the magnitude of alpha 25 is going to be equal to alpha times the magnitude of 25. The magnitude of 25 is root 29. So this entire magnitude is going to be equal to 20 over 29 times the root of 29. That gives root 29 at the denominator. So therefore, the shortest distance between 5, 2 and this line 2x plus 5y is equal to 0 is the length of the projection of v onto the direction of 2, 5, which is perpendicular to the line, and that length is equal to 20 over square root of 29. Alright, so that is part E. And last but not least, let's move on to part F. So now let's come back to part F, which is re-recorded because of a footage problem. So let's look at F, and also the solution file has a bit of a typo, so it will be a little confusing to reference that at the same time. But in part F, suppose I have the following set of vector H, which is the vector of all x, such that w dot x plus 4 is equal to 0. W is orthogonal to any vector in H. Find the closest distance between this set of vector and the points 10, 11, 2 in terms of W itself. Let's suppose that H, this set of vector, is actually a plane, such that I'm going to have a vector that starts from some point on H and ends at the point 10, 11, 2, and if I project this vector onto H, I will notice that their difference must be perpendicular to H. So this perpendicular distance, this perpendicular vector, the difference between x, which I'll call this vector, that reaches 10, 11, 12, and the difference between x and projection of x onto H is perpendicular to H itself. I'm going to call this y, and this is also going to be equal to this has to be a multiple of W here. So let me call the vector at the bottom D, which would be the projection of x onto H. And I'm calling it D so that it's easier to reference later. But one lesson that we can take is that, first of all, x minus d is equal to y, which must be a scalar multiple of W. And second of all, we can notice that x minus d dotted by W is equal to alpha w dot w. And this is also being equal to x dot w minus d dot w. So keep in mind that d dot w is, according to our definition of the set, since d belongs to the plane, d dot w plus 4 must be equal to 0. So d dot w is actually negative 4. So this is actually equal to x dot w plus 4. And we know that x is equal to 10, 11, 2, but we'll substitute that in later. Meanwhile, the right-hand side is equal to alpha w length squared. So in the end, we can see a definition of alpha appearing as alpha is equal to 10, 11, 2 transpose w plus 4 over the square of length w2. So now keep in mind that alpha is the coefficient here of w if alpha w is going to be the difference between x and its projection, such that y is equal to alpha w. So we're actually trying to find the magnitude of alpha w in this question. The magnitude of alpha w is equal to alpha times the magnitude of w. So that's going to be equal to, well, there's a magnitude of w in the denominator of alpha 2, so I cancel it out. So at the end, I reach this expression that is 10, 11, 2 transpose w plus 4 over just the length of w. So there we have finished all parts of the question. The takeaway or the mathematical skills that this question is trying to teach is how to set up your proof and how to gain information by drawing out things. And at the same time, it's also a practice problem on how to leverage different properties of projection to complete some interesting proofs, or for example, to find an easier way to find the shortest distance between a point and a line or a point and a plane. So I will post the screenshots. I'll pause the video at some screenshots of the previous parts and end the recording here. Have a nice day.